We are going to transition from functions on the natural numbers to functions on the real line. We will use a lot of ideas that we've developed on sequences to get us started, but the more common and more intuitive approach to continuity is to use the epsilon delta formulation. In this video, we will look at the two formulations of continuity and then prove that the two formulations are equivalent. The intuitive idea of continuity is that the graph can be drawn without lifting your pen from the paper. The graph on the left is a continuous function at x0, but the graph on the right is not. The jump in the graph is what creates the discontinuity. While this is the easiest type of discontinuity to visualize, we will later see that this isn't the only type of discontinuity. This is the first definition of continuity. Definition 1. Let f be a real-valued function whose domain is a subset of R. The function f is continuous at x0 in the domain of f if for every sequence x sub n in the domain of f converging to x0, we have the limit of f of x sub n equals f of x0. To keep things simple, we will assume that the domain of f is just the real line. Let's return to the graphs and try to get an understanding of what this all means. Let's focus on the graph on the left. Suppose we have a sequence x sub n converging to x0. This is a convergence of points along the x-axis. For each point x sub n in the sequence, we evaluate the function at that point to get a point along the y-axis. This is f of x sub n. The definition of continuity states that as x sub n approaches x0, we have f of x sub n approaching f of x0. We can see what goes wrong if we look at the graph on the right. Here, as the values x sub n approach x0 from the left, the values f of x sub n are going to hit a ceiling and never get close to f of x0. There will always be a gap there. This is the basic idea of continuity using sequences. We can understand continuity without needing to use sequences. Here's the alternative definition. Definition 2. The function f is continuous at x0 if, for every epsilon greater than 0, there exists a delta greater than 0, such that x in the domain of f and absolute value of x minus x0 less than delta imply that the absolute value of f of x minus f of x0 is less than epsilon. This definition gives us a big hint as to its relationship with sequences because it's another epsilon definition. However, instead of a capital N where we look at little n bigger than capital N, we have a delta where we look at absolute value of x minus x0 is less than delta. All this means is that we're looking for x that are close to x0. Let's go back to the graphs one more time. This time we will draw an epsilon band around f of x0. The challenge is to find a vertical delta band such that the entire part of the graph inside of the delta band is also contained within the epsilon band. We can see that on the first graph, if we shrink the epsilon band, we will always be able to shrink the delta band to keep everything inside. However, for the second graph, if we make epsilon too small, there will always be a part of the graph that's outside of the epsilon band. We will now prove that these two definitions are equivalent. Theorem: the two definitions of continuity are equivalent. Suppose a function f is continuous according to definition 1. We must show that it satisfies definition 2. We will use a proof by contradiction. This means that we will assume f satisfies definition 1 but fails definition 2. How does it fail definition 2? Let epsilon be greater than 0, but suppose no delta can be found such that the absolute value of x minus x0 less than delta implies the absolute value of f of x minus f of x0 is less than epsilon. In other words, for any delta, there exists an x such that the absolute value of x minus x0 is less than delta, but the absolute value of f of x minus f of x0 is greater than or equal to epsilon. You may want to pause the video right now and just take a moment to think about it. The statement below will help you to organize the information in your head. Now let delta sub n be any sequence of positive numbers where the limit of the delta n's is equal to 0. Then each delta n can be used to generate an x sub n such that the absolute value of f of x minus f of x0 is greater than or equal to epsilon. This creates a sequence x sub n such that the limit of x sub n is equal to x0, but the limit of f of x sub n is not f of x0, and this violates definition 1. Therefore, the function f must satisfy definition 2. We will now prove the other direction. Now suppose f satisfies definition 2. Let x sub n be a sequence converging to x0. We need to prove that the limit of f of x sub n is equal to f of x0. In other words, for any epsilon greater than 0, we must find a capital N such that little n greater than capital N implies the absolute value of f of x sub n minus f of x0 is less than epsilon. So let epsilon be greater than 0. By definition too, there exists a delta such that the absolute value of x minus x naught less than delta implies f of x minus f of x naught is less than epsilon. Since the limit of x sub n is equal to x naught, there exists a capital N such that the absolute value of x sub n minus x naught is less than delta for all little n greater than the capital N. Therefore, we also have that absolute value of f of x minus f of x naught is less than epsilon for all little n greater than capital N as required. This highlights the essential features of continuity. Proving that specific functions are continuous is a lot like proving sequences converge. In class, we will go through some examples of this and use many of the same techniques that we saw in previous sections.